Hello friends. Uh, in this presentation, we are looking the method relative velocity and acceleration method having the Corolis component of acceleration. So this is the method which comes in unit number 6. So you know unit number 6 is having the two methods, graphical methods. This is a relative velocity and acceleration method having the Corolis component, and the second one is the Clean's construction. So uh, the method that we have seen in unit number 5th, that is the relative velocity and acceleration method. So again, by taking the help of that method and by adopting the different steps given in that method that we have seen for analysis of simple mechanism, almost 90% of that particular process we are following for this particular relative velocity and acceleration method having the Corolis component, and the 10% is change that we are looking. And then after looking some features of that Corolis component, we are taking one problem where the Corolis component comes into picture. Now in previous method, that is relative velocity and acceleration method, which is the method of unit number 5th, we have seen that the acceleration of a moving point is relative to the fixed body, and that have the two components. One is normal and another is the tangential component. And we have seen how to find out the magnitude as well as direction and how to apply these particular two components for making the acceleration polygon in a previous method. But in some cases, the point may have its motion relative to the moving body. In earlier case, the acceleration of a moving point relative to the fixed body. But here, sometimes in some cases, the point may have its motion relative to the moving body. So, for example, in case of quick return mechanism or the slotted lever mechanism, oscillating cylinder mechanism, you will find the motion of a point relative to the moving body. And because of this particular problem, the Corolis component comes into picture, and that's why we are now we are and the question is how to determine the magnitude of the Corolis component, how to determine the direction of the Corolis component, that comes under the 10% changes. Otherwise all 90% process of making the acceleration polygon is same that we have discussed in relative velocity and acceleration method. Now to see this particular thing, let us take the problem of quick return mechanism. uh, Quick return mechanism shown in figure. The OA is the driving crank and it is rotating at 120 rpm in clockwise direction, and the different lengths are shown in figure, from which you can easily draw the configuration diagram. QC is given, length of QC is given 150 mm, the length of OA is given 200 mm, and from this given information, the unknown is the magnitude and the direction of angular acceleration of slotted bar QB. So the QB is the slotted bar and whose magnitude and direction is to be determined is the question. So before let us see how to solve such problem. So it is again the problem of uh, we can say the slotted lever mechanism, crank and slotted lever mechanism. So definitely the Corolis component is coming into picture. Uh, Before discussing that, the The step number one is to make the configuration diagram as per the scale. Here I have taken the scale 1 centimeter is equal to 50 mm. Accordingly, you can make the configuration diagram. Then again, you have to make the velocity polygon, and for calculating for plotting the velocity polygon, it is essential to determine the velocity of crank, and the velocity of crank comes 2.513 meter per second. You take the scale for velocity polygon. Here I have taken the scale 1 centimeter is equal to 0.5 meter per second. So by the same process, you can make the velocity polygon. First of all, you fix the fixed point O and Q. O and Q is the fixed point. Then, as per the direction of crank OA, which is given clockwise, you take the velocity of link OA in clockwise way. So from small OQ, you take the velocity uh, direction, and magnitude is 2.513 divided by scale, so it is approximately 5.1 centimeter. So you take the 5.1 centimeter length of the vector OA according to the direction of rotation clockwise. You take the distance from bottom or downside, so O and Q is upward, and you take the 5.1 centimeter downside, so you give the name as A. Then you go now the change is only that velocity polygon. You have to determine the velocity between A and B. So A is the point of the name of the point on the crank OA. Crank is OA, and B is the name of slider which is sliding along with the in the bar. Okay, so this slotted link is moving along with the slider is sliding. So here the slider I have given the name as B, and by default A is the OA is the crank. So the velocity comes into picture, that is the velocity in between A and B. So it is always parallel to the link on which the slider is sliding. So accordingly you take the parallel, that is the velocity of A with respect to B. So you will get the direction is you are getting the direction that is parallel to link on which the slider is sliding, but you don't know the magnitude. So you that then you go for another link QB. So the velocity of link QB is perpendicular to link QB. So from the fixed point you draw the velocity, and then you will get the small b, and the point C lies on link QB. So as per the proportionate method, you can easily locate the point C on the link QB. So after making the velocity polygon, uh, again the next one is to make the acceleration polygon. And before going to make the acceleration polygon, you have to summarize the different informations of the given link as we have done in the earlier problem. That is a link, then the length, velocity, the normal component, the tangential component, and then the Corolis component. So here for the given problem, the links are mentioned here. The link OA, the second link is BA, the third link is BQ. So the length are mentioned here. Velocity is written from the velocity polygon. Then the normal component by usual we have defined here. The tangential component is given here, and only the change is that for the link BA. So because here for BA there is a Corolis component comes into picture. So how to determine the magnitude of the Corolis component? We have the formula 2 times sliding velocity into omega, that is angular velocity on which the slider is sliding. So here by using that formula you can easily determine sliding velocity, you know, from the velocity polygon, and omega. Okay, so by doing that you will get the Corolis component magnitude and the direction. Okay, so that for direction we will see later. So in this way we can determine the magnitude of the Corolis component in bit for the link BA. So only this particular magnitude and how to locate the direction is the changes that comes in the 10%, and otherwise the overall process is same. Now let's see the acceleration polygon. So again, by we have to find out the normal component for the crank. It comes 31.57. So by taking by based on that value of the normal component of the crank, you take the scale 1 centimeter is equal to 4 meter per second square. So you locate the fixed point O and A. Then draw the vector OA, which is parallel to capital AO given in the space diagram. So which is the normal component of AO. So you take this particular magnitude, which is 31.57 divided by scale. So almost it comes 7 point something centimeters. So you take the 7 point something centimeter length as the magnitude for normal component of crank, and the tangential component is 0 because the crank is moving with uniform speed. So you got a point. So from A, draw the vector AB dash. So it is the Corolis component. So this Corolis component, how to determine the magnitude you got from the formula, that is 16.25. So 16.25 divided by 4, that is scale, that is 4.1 centimeters. So magnitude you got. Now how to find the direction of the Corolis component? It is we have four possibility, and it depends on the sliding velocity, right, omega of link on which the slider is sliding. So this particular velocity AB, it is outward, okay, with respect to q, with respect to fixed point, and the direction of omega of bq is clockwise. Okay, it is clockwise because when you move this sliding velocity vector by 90 degree as per the direction of omega, you will get the direction of Corolis component. So by moving the sliding velocity vector of AB as per the rotation of omega by 90 degree, you will get the direction of Corolis component of AB. So in this way you are getting the direction of Corolis component. So by taking the magnitude and the direction, you will get a B dash. You can also write down X. So it is not final component. So then another component of the Corolis component, another component for link AB is the normal component, which is perpendicular to the Corolis component. So you don't know the magnitude, but the direction you know of the normal component of AB. So you that. Then you go for the another link QB. Again by the same process of normal and the tangential component of QB, the normal component of QB, it is towards the center of rotation. The magnitude you know, then you got B double dash, and again you take the tangential component of BQ, which is perpendicular to the normal component of BQ, and this the tangential component of BQ and the normal component of AB, where it is intersecting. I have given the name as small b. Okay, so you can connect this B to the small a, and that is the final component of AB. So the Corolis component and normal component of AB makes the final component of AB. So in the same way, by joining the small b with fixed point, you will get the final acceleration of link BQ. So the normal component of BQ and the tangential component of BQ, and this is the final component of BQ. Accordingly, you have to give the direction. So in this end, you have to locate the C point as usual. We have done earlier problem by using the proportionate method. So in this way, you have to draw the acceleration polygon. And what is the unknown? The unknown is the angular acceleration of link BQ. So we have the formula. The tangential component of BQ is equal to length of BQ into alpha of BQ. So the tangential component of BQ is found out from the acceleration polygon, and which is b double dash b. So you take measure the length of b double dash b, you multiply by scale, it comes 7.2 meter per second square. You put up keep that value in the equation, you will get the final equation, final value of alpha, that is angular acceleration of link BQ, which is 27.69 right per second square in anticlockwise. So in this way you have to solve this Corolis component problem or such mechanism. Thank you. Thank you.